Welcome to this series on linear algebra for business analytics. In this video, we're going to look at the notion of dot product and the notion of matrix multiplication. Matrix multiplication. So, if you recall, in the last video, we introduced the notion of linear transformation. And we described how a linear transformation transforms vectors to vectors. And in particular, if we know how the linear transformation transforms the basis vectors, in particular, if we know how the linear transformation makes a basis vector such as 1, 0, 0, 0, 1, 0, and 0, 0, 1, for example, in 3 dimensions, how does it transform each one of them into a resultant vector? Then we can stack these three vectors in next to each other as columns and create a block which we call the matrix. And this is the representation of the linear transformation. And in particular, for any vector in the input space. So, for example, if the vector is x, y, and z, and this matrix, let me denote it by a capital letter A. In this example, for example, if the output vectors are in 2 dimensions, then the A matrix is a collection of 6 numbers. Let me just call it A, B, C, D, E, F, which take the vector x, y, and z, and A is this matrix, sorry, which take the vector this and produce an output which is going to be 2 dimensions, maybe u and v. Okay, so I'm using a lot of alphabets, but just imagine that, and we also figured out how it actually multiplies. In fact, the multiplication is just as x times AD plus y times BE plus z times CF, and then you do the vector addition, the linear combination stuff that we discussed a couple of videos ago. So, this was the notion of linearity, that a function acting on an input, it can act on the parts of the input, which is what the basis functions kind of, basis vectors kind of can decompose xyz, right? So xyz is nothing but x times 1, 0, 0 plus y times 0, 1, 0 plus z times 0, 0, 1, right? So because we know how the function acts on the basis vectors, we also know how the function acts on xyz as well because of linearity. So check out the previous video. And now let's move on to dot product. A dot product is nothing but a special case of a linear transformation where the output is one dimension. So far, actually, I've not discussed what a one-dimensional vector is, but think of a one-dimensional vector as as a number, for example, 10, or for example, minus 3.3. So these are one-dimensional vectors, which are nothing but, I guess, scalars. And we want a transformation A, which takes, let's say, a 3-dimensional vector and produces a 1-dimensional vector, right? So how does then A look like? A would be, for example, A, B, and C be the entries or columns of A, and then it would multiply with a generic vector x, y, and z, and then it will produce a vector which is going to be x times A plus y times B plus z times C as the single entry in that matrix, in the resultant in the resultant vector. A single entry is the resultant vector. Okay, so this is the this is dot product. So there's actually a lot more interpretation in terms of projecting projections and duality and so on, but that geometric viewpoint you can definitely, certainly, certainly look at it after this, maybe after this video. Um, okay, so if you look at this, this is a matrix, but it has 3 columns, but it has only 1 row. So this is actually also related to the vector A, B, and C. So there's this notion of duality that I urge you guys to check out. So this matrix is related to this vector A, B, and C. Okay, and so what is the dot product? So why are we even looking at dot product? Why is this special case that interesting? Is that this dot product allows us to find the um, directionality of a vector with another vector, and in particular this vector is A, B, and C. So a dot product, or essentially this particular transformation, which is related to the vector A, B, and C, allows us to understand how the input vector, in this case x, y, and z, is related to A, B, and C in terms of directionality. Is it are both A, B, and C and x, y, and z? If you, I mean, in 3 dimensions. I want to draw the 3 dimensions, but let's say this is the first vector, and this is the A, B, and C vector. Dot products lets us understand if both these vectors are almost facing in the same direction. Maybe one is very direct, is pointing in a different is pointing in a very different direction. That's what we can interpret from dot products. And let me quickly add a note about matrix multiplications. Because as we know, linear transformations are matrices, and we know that if I want to, so let's think of this, right? So let's say there's an input, and we transform it to an output, and we further transform it to another output. Okay, output 2, and this is output 1. So in general, for functions, this is just called function composition. Okay, in particular, let's say this is function f1 and this is function f2. Then let's say this input, a generic input is x, a generic output we don't have to even denote. So let's say f of x is the value, function value at x. Then, sorry, f1 of x would be the function value of function f1 on x. And then we just take that as input to the second function. Okay, this is called composition of functions, where you apply the first function f1 first, and then you apply the second function f2. Okay, now similarly for matrices, which are linear functions for vectors, we also have the same idea. We can take a matrix, okay, second matrix, which transforms the first matrix, which the output of the first matrix, and the first matrix works on an input vector x. Okay, so given an input vector, first I apply first matrix, and then I apply the second matrix, and in between I get a vector, right? So matrix multiplication is nothing but applying the first matrix to an input, and then transforming the transforming the input vector to an intermediate vector, and then the intermediate vector to another vector. So it's like saying I have an initial vector, x vector, and I first transformed it to an intermediate vector, maybe y, and then again I transform it to another vector z. Okay, so that's what matrix multiplication or the combined effect of this linear transformation is. Okay, ultimately it is a transformation from a vector to another vector. The overall transformation is from vector x to vector z. Okay. And actually there's a nice trick. Sorry, there's a nice trick to think about this. So let's say matrix M2. So let's say matrix M1 is actually, let me explicitly write it as some vector v1 and then another vector v2, right? Remember, if let's say in 2 dimensions, we know that v1 is the transformation of the first basis vector and v2 is the transformation of the second basis vector. Remember, e1 and e2, right? So, and then, let's say this is the M1 matrix, right? Not these two, but this was the M1 matrix. Then, I want to know M2 times M1 times some input vector, let's call it x, right? I can, for now, ignore the input vector x and actually think of what does matrix multiplication mean. I want to multiply M2 with M1. That is as good as saying, okay, let me think of multiplying M2 with V1 and M2 with V2. Okay, so M2 with V1 and M2 with V2, right? And then there's the input x vector that I anyway have to multiply. So M2 times V1 is going to be another vector, right? M2 times V2 is another vector. And at this point, we know exactly how M2 can act on V1 if we know how, if in whichever space, input space V1 and V2 are, if we know their basis vectors and how M2 transforms, how the second transformation, linear transformation transforms those two basis vectors, then there'll be a block of numbers corresponding to that transformation. We know exactly how this multiplication happens. So first we multiply this with the first vector, this with the second vector, and then the overall, we get two vectors, and then we multiply with x, for example. So this is an example of matrix-matrix multiplication. Anyway, so coming back to, I just want to end this video with a couple of examples of why dot products are interesting. And the first example is actually, again, back to, let's say, binary classification. In business analytics or machine learning. So remember, I had given an example where I had data points which are feature vectors, and there was a hyperplane, and there were another bunch of feature vectors. These are all data points, and of course, binary classification is trying to find certain models in binary classification. For example, logistic regression. They try to find a linear linear decision boundary. Okay. Or let's think of a support vector machine. It essentially, for binary support vector machine, for binary classification, tries to find a hyperplane that separates the two classes, in this case the circles and the pluses. And a hyperplane is actually, remember, a hyperplane was the span of a bunch of vectors which didn't span the whole dimension, whole space. So the hyperplane is essentially characterized by a vector normal to it, and then we can actually talk about how different. So there's a vector normal to the hyperplane which completely characterizes the hyperplane. Normal to the hyperplane just means it's perpendicular to it, okay, in geometric sense. And then we can talk about we can actually ask whether this plus point, we can ask about the directionality of this plus point, whether the plus point, the direction in which the plus point lies, how is it different from the direction in which this circle lies. And you'll see that those two directions are going to be far away from each other, the directions of them. whereas the directions of two plus points would be very close to each other. Okay, so that's something that a dot product can tell you. And another example of dot product, which is actually very interesting, which you wouldn't think of a dot product, is finding an expectation. Right? So um, so what do I mean by that? Let's so for this you want to check some reflection on probability and statistics. So let's say there's a random variable. I'm going to denote it as z, which takes let's say three values: -1 with probability 1/2, 0 with probability 1/3, and 1 with probability 1 minus 1/2 minus 1/3. Okay, then the expectation of z, expectation of z is gonna be this is a standard notation to represent an expectation, is going to be equal to this dot product, which is -1, 0, 1 times what is that? 1/2, 1/3, 1 minus 1/2 minus 1/3. Okay. So an expectation for, in this case, a discrete random variable can be thought of as a dot product between what is called a probability mass function, or basically a probability vector, and the what is called the support of the random variable. So that's all for this video. Thank you for watching.